polynomial. And a polynomial is going to be, what's the domain going to be?
All real numbers.
All real numbers, yes. So it's defined everywhere. Great. Intercepts. What's one of the what's the easiest one?
Y.
Yeah, so when x is 0, y is 1. So that's your y-intercept. And then you want to solve for your x. So that's your y-intercept. We want to solve for the x-intercepts. How do you solve for the x-intercepts?
Don't even try.
Oh, come on. You guys are big kids. This ain't like Algebra 2 anymore, kids.
It ain't.
No, no. Although Algebra 2 kids, I hope they could do this, but they probably can't because we don't go quite that high with the polynomials. So this is our y-intercept. We want to go for our x-intercept, so we set it equal to 0. What do? You try to factor this. Exactly. You try to factor it. You try to factor because theoretically, if you're sketching this thing, you're not using your calculator. Theoretically, right?
Yeah.
Okay. How do you factor this?
Use your calculator.
No. Ballsy. That's good. I like that's good. Nice. Come on. How do you factor this?
Use synthetic division.
Synthetic division. Right.
Nothing
synthetic.
works.
Nothing works.
Literally. Like look at the numbers that.
Literally nothing works.
No,
literally.
Those are the three numbers that are the intercepts.
So first of all, you need the potential rational zeros, and this is where some kids fail on this.
Yeah, I don't.
Because you need to list all the potential rational zeros. What are all the factors of the constant? Plus or minus what? 1. That's the constant. What are all the factors of the leading coefficient? 1 and 2, and you have to do plus or minus. So what are all the potential rational zeros? Plus or minus what? 1 and a half. So how many potential rational zeros are there? 4 of them. They all have an equal probability of being true, but once you find one of them, things get much easier. Like you chip away at it, right? So you should test the ones that are easiest to test. Which ones are easiest to test? Positive small ones that are whole numbers. So start with 1. What are the coefficients of this polynomial? I'll give you a start. 2, 0, 0, 4, 3, 2, then what? 0 and 1. So you start with 1. You drop the 2 down. What do you multiply by? 1. You get 2, 2, 2, 2, 2, negative 3, negative 3, negative 3, negative 3, and so that's the remainder. When you evaluate, when you plug in 1 into this, 2 minus 5 is negative 3. Negative 3 plus 1 is negative 2. Therefore, is x minus 1 a factor?
No.
No. Do you erase at this point? No. Do not erase. What do we test next? You want to test a half? Sure. Let's test a half. 2. What do you get? So it's 2, 0, 0, negative 5, 0, 1. You get 2, 1. 1.
1 half.
1 half. 1 half.
1 fourth.
1 fourth. Negative.
Negative, it doesn't
4
work.
and 3/4. Blah. Blah and
Blah.
blah. Does it look like this is going to work?
No.
No. Okay, so we tested that. So did you test negative 1 as well?
Nope.
Let's try negative 1. 2, 0, 0, negative 5, 0, 1. You get 2. What do you get next? Negative 2, negative 2, 2, 2, negative 2, 7, 7, 7, negative 7, and?
Negative 6. Yeah.
Negative 6. Ooh. So what's the last thing we should test?
Negative 1 half.
Negative a half. And what happens on this one?
It blows up.
It blows up. So what do we tentatively conclude? No rational zeros. Okay. Are there tons of other pieces of information we can get about this thing? Yes, absolutely. There are tons of other pieces of information. So let's go on. We tried to find the x-intercepts. First of all, are there any x-intercepts?
Yes.
You know there has to be at least one. Why?
Because
you automatically know there's at least one.
Because it's an odd function. Well,
it's an odd-powered.
Yeah, it's an odd.
It's an odd-powered polynomial. So therefore, it either goes like this or like this for its general shape. So what does it have to cross?
Yeah,
And it's nice. I'm using to you in the morning. This is good.
Yeah,
has to cross the x-axis. How many times could it cross?
5.
A million.
4. 4.
No, 4 times. 1 less than the degree, right? A quadratic. Sorry, it could cross 5 times. Sorry.
Yeah.
So a quadratic could cross how many times? 2. A cubic could cross 3. A fifth degree could cross 5. But we know that we think that none of them are rational because we tested all of the potential rational zeros. Does this mean we just stop and give up?
No.
No, we don't stop and give up. We keep on going. So what's the next thing? DIS, which stands for we do f of negative x And this is going to be, what's the original question? It's 2 negative x to the what? 5 minus what? Minus 5 times negative x squared. Yep. Plus 1. So what do we end up with? Negative 2x to the 5th minus 5x squared plus 1. Does that does not equal negative f of x, right? And it does not equal f of x. It either doesn't change or it flips the whole thing. So therefore this is what?
No, not symmetrical.
It's neither. Well, it might have some other symmetry, but it's neither. And when you say neither, it means neither even or odd. Now here's the thing. Those are bad labels in a way because we think of even and odd as integers, and if something isn't even, it has to be odd, or vice versa. In this case, you can have neither odd or even. Odd means it's symmetric over the origin. So symmetry, okay, no. What's the next thing we need to test? Come on, what's the next thing? So first of all, we look at the limit as x goes to infinity of f of x, of our function. As x goes to infinity, what does this function go to? It goes to infinity. I don't really like saying equals, but it goes to infinity. It gets infinitely big. What's the limit as x goes to negative infinity of this thing? It goes to, I'll do that, negative infinity. So is there a horizontal asymptote?
No.
No HA, no horizontal asymptote. Now what about vertical asymptotes?
There's
None.
no.
Why?
Because you don't have a denominator.
There's no division, exactly. There's no division of polynomials here. So there's no vertical asymptotes. Okay, that's great. What's next?
Increasing and decreasing.
Increasing, decreasing, right? So what do we look at for increasing, decreasing? First derivative. So f prime of x is going to be 10x to the fourth what? Is it just minus 10x?
Yeah. Yep.
Yeah, it is. Minus 10x, exactly. Great. So we want to know where it's increasing and decreasing. So what do we solve for first?
0.
0 is a noun. Yes, we solve for 0. What does that mean? We plug 0 in. We set it equal to 0 and solve. So we have 10x to the fourth minus 10x is equal to, what can we factor out?
10.
And x, right?
Yeah.
So you get x cubed minus what? 1 equals 0. So first of all, what's one number you know is... What's one number you know? You know 2, actually.
1 and 0.
1 and 0. You know x is equal to 0 and x is equal to, or 1, right? But is there another one? Can it be negative 1? Can't be negative 1, but we know that 1 factors into that. So what do we need to do to this? What do we need to do? We need to factor it. We know one of the factors, though. We know 1 goes into it nicely, right? What are the coefficients of x cubed minus 1? 1. 1. So you get 1, negative 1, thank you. That's important. So you get 1, 1, 1, 1, 1, 1, 0. So what's the factor form? X cubed minus 1, therefore equals x minus 1 times what? Plus 1. Exactly. Now we ask ourselves, what are the zeros of that? Can this equal 0? Can x squared plus x plus 1 equal 0? It can. It can, but only when what? This can equal 0. There is an x value. There's 2 of them that work, but they are what? Yes, we suspect they are imaginary. How would you guarantee that they are imaginary?
Quadratic function.
Just use the quadratic formula, right? B squared minus... Oh, so maybe we're wrong then. B squared is going to be 1 minus 4 times 1 times 1. The discriminant is therefore going to be what? Therefore, it's going to be imaginary, right? So what do you end up with? If we did this out, you would end up with negative 1 plus or minus I root 3 all over 2. Those are the other 2 zeros. Those are definitively what? Imaginary. They both have I in them. So the intervals of increase and decrease, we have 0 and 1, right? Those are the x values. And we want to do f prime of x, right? At 0 and 1, what are the values of the derivative? So what do we need to test? Values?
Between 0.
Yeah, and we have, remember we have this. We have 10x times x cubed minus 1. That's our derivative, right?
Yeah.
Write the derivative out right next to it and just think to yourself, if you plug in a really, really big negative number, it's going to be negative 10 times that negative thing cubed. Is that going to be negative or positive?
Negative.
Negative times a negative is a?
Positive.
Positive. Thank you. What about a huge positive number? A positive number times 10 times a positive number cubed?
Positive.
Positive. Now, what do we need to plug in? What's a good thing to plug in the middle?
1/2.
Plug in a half. 10 times a half times 1/2 cubed minus 1. Well, this is going to be what? 5, and that's going to be 1/8 minus 1, which is what?
Negative.
Negative, so the middle is going to be?
Negative.
Negative. So where's this thing increasing?
0.
Negative infinity.
0.
Do you include 0? No, and where else is it increasing? 1 all the way to, can't get to, but you say those open intervals, right? And where is it decreasing? 0 to 1. Exactly, right. So now we have the intervals of increase and decrease, which leads us nicely into the next step, which is what? Nope. Don't jump something. We haven't figured out where the...
Oh.
Max and mins, thank you. The mins and maxes, right? And we actually know where those are now because... We know the x values because we did the intervals, right?
Yeah.
So if it goes up and then down, what happens right here? What does that have to be?
That has to be a max.
If it goes up and then down, we know that there has to be a max here. And then if it goes down and then up, it has to be a min. So we know that there's a max at x equals 0 and a min at x equals 1, right? Well, that's just the x value. We'd also like the what?
Why?
If it's x equals 0, it's 0, 1, I think, right? And if x equals 1, is it negative 2? Yeah, we figured that one out, right? It's negative 2. So we have the mins and maxes, right? Okay, what's next? We found our mins and maxes. What? Concavity. So if we want concavity, what do we have to look at, Bissell?
We have to look at the second derivative.
Thank you. And we knew that f prime of x was what? 10x to the minus 10x, right? So what's f double prime going to be?
40x minus 10.
40x cubed minus what?
10.
10. And we're particularly in the inflection points are where the second derivative changes sign. No, not where it equals, it's where it changes sign. Remember, just because the second derivative is 0 doesn't mean it necessarily changes sign. It doesn't have to. So we set it equal, though. We set it equal to 0. If we're going to solve this, what should we do first? If it was me, I would factor out 10 and make it 4x cubed minus what? Equals 0, right? So we know that if we're going to solve this, 4x cubed has to equal what? 1. So x to the fourth has to equal 1/4. So x is equal to what? The cube root of... You can say the cube root of 1/4, exactly.
Or you can do 1 of 4. Yeah.
Why don't I do plus or minus?
Because it's a cubic function.
Yeah.
Well,
It's not a cube root, it's an odd one. There's only one, right? So how many times does this thing change concavity? Once at an x value of 1 over the cube root of 4, which is like 1 point something, right? So it's like pretty close to 1-ish.
Yeah.
Okay, so we just did this. No, actually, we don't know if it changes concavity. What do we need to actually do? Actually test it, right?
Points on either side.
X f double prime of x. So we have this value, which is 1 over the cube root of 4, right? And we know the second derivative comes out to 0. And what was the second derivative? It was 40x cubed minus 10. If I plug in a negative number, that thing is going to be negative. If I plug in a positive number, that thing is going to be positive. So this thing concave down all the way to an x value of 1 over the cube root of 4, which is about, it's less than 1, right? It's going to be less than 1, but it's also greater than, a half, for example, just so you can estimate it in your head. And we know it's going to be concave up the rest of the way. Does this make sense, everybody? So at this point, what should we do? Graph it. Let's just put together what we have. What do we have here? This thing is continuous. It looks like an S-curve. What points do we definitely know are there?
Except the one,
0, 1, right? Correct?
yeah.
And 1 what? So that's 1. And 1 what? Negative 2? Like this? It's a min and then a max, right?
Mm-hmm.
We know what the general shape of this thing is, and there are no asymptotes. So we know that this thing is, we can adjust this as we need to. We know it's going to go up, right? And then what's it going to do?
Okay.
It's going to go down, and then what's it going to do?
Come back up.
Come back up, exactly, like this. Now here's the thing. We need to make sure it matches all the other aspects. Well, is it increasing from negative infinity all the way up to 0?
Yeah.
Yep. Is it decreasing between 0 and 1? Yep. Is it increasing from 1 all the way on?
Yeah.
Yep. So it matches first derivative. Concavity-wise, though, here it is. This is where it's concave down, and then right about there it changes to concave up. Is that changing concavity? Is that happening at about A little less than 1?
Yeah.
Sure looks like it, right?
It's close
Now
enough.
I could ask you though, what's one thing I could ask you about the change in concavity? We know the x value. I could also ask you for the
Y thing.
y value. So I could theoretically ask you, what is the point of inflection? What is the point of inflection? So you'd have to find this point. How do you find that point?
You plug in
Yeah, you plug in
1
the
over the cube root of 4.
4 into what? The original function. I see that happen all the time. People plug it into the wrong one. They plug it into the first derivative. What was the original function?
2x.
2x to the fifth.
5x squared plus 1.
Plus 1, right? So theoretically you could plug it in, but that's the kind of thing, if you wanted to get a numeric value, what would you need?
Calculator.
You'd really need a calculator for that. You'd really need a calculator. Okay, so you could find it. Now, at the end here, what would be something that, there's one last thing. Let's say you get totally lost and you had no idea, like you needed some more information. What can you always do if you want?
Set for 0.
Yes, okay, you can always do that, but let's say you do all these steps and you still want more information about the function. What can you do that's the easiest thing you can do that gives you some concrete information about this function?
Like it's like calculus.
No, without using your calculator. What? What does that mean? What do you mean plug in points? For? So make a...
Make a
Table.
table.
Yeah, so basically either, like, just plot more points. If you ever want more information, plot some points, right? So if I plug in a really big number into the original function, you know there's going to be a point down here and a point up here. So that gives you some information. If you're ever stuck, like completely stuck, plot some points. I'm totally serious. It also helps you know if the information you put on your graph matches reality, right? If you're doing something and all of a sudden it just doesn't match, go back and reevaluate. But don't forget, you can always plot points. I mean, if I gave this function right here, and I said to my Algebra 2 students, if I had Algebra 2 students, graph this, what would they have to do?
Use a calculator.
No, they don't have a calculator. They would make a what?
Table.
They just make a table and connect the dots, right? Theoretically, if they plot enough points, could they make a really nice graph?
Yeah.
Yep.
Yeah, they could. So don't forget how you would do this if you didn't have calculus. Just because you have calculus doesn't mean that's the only thing you use.
Hammer.
Yeah, hammer. Hammer's back. Hammer's back. Okay. X such that x does not equal 0. Nice. Intercepts. When x is 0... Oh, well, it's undefined, so you can't do that, right? Yep, nice, nice, nice. So it's when x squared minus 2 is equal to 0. So that's when x is equal to plus or minus root 2. So our two x-intercepts are going to be root 2 comma 0 and negative root 2 comma 0. Exactly. Domain intercepts symmetry. Let's do symmetry. What do you plug in? No. F of negative x. You never plug in a value. Just because it's symmetric for one value does not mean it's symmetric for any others. F of negative x is going to be negative x squared, like that, minus 2 over the fourth. You end up with x squared minus 2 over x, which is f of x, right? Which is f of x. So therefore this thing is even. That's awesome. That's helpful. That basically means if you can graph half of it, you have the other half. Domain intercepts symmetry. What's next? Is it asymptotes next?
Yeah.
Yeah.
So what for horizontal asymptotes, what do you look for? What do you look at?
As x goes to infinity.
Yes, you look at the limit as x goes to infinity of f of x. If x goes to infinity, what does this thing go to? It goes to 0. And you also want to think about this too. As it goes to negative infinity, what does it go to?
0.
It also goes to 0. That's correct. So we know there's a horizontal asymptote, and there's only one of them. What about vertical asymptote? X equals 0. That's correct. At x equals 0. Because is it a removable discontinuity at x equals 0? No, because it doesn't cancel. It doesn't cancel. What's after asymptotes?
Increasing, decreasing.
Increase and decreasing, right? So let's talk about increasing first. Well, it's increase, decrease. What do you have to look at for this?
The derivative.
The first derivative. Be specific. Let's be very specific. So f of x is equal to x squared minus 2 over x to the fourth. If we take the derivative of this, what's one way we could take the derivative? Let's do the quotient rule. Sure. F prime of x is equal to low d high minus high d low all over x to the 8th. Exactly. Could we clean this up a little bit? Sure. 2x to the 5th minus 4x to the 5th plus what? 8x cubed all over x to the 8th. So what does this become? Negative 2x to the 5th plus 8x cubed all over x to the 8th, right? So therefore, why are we looking at this? Because we want to know where the first derivative is equal to 0 or where it's...
Increasing.
Okay, hold on.
Or where it's undefined.
Or where it's undefined. Those are called what? The
The
critical points. So this thing is undefined where? Hold on, could we simplify this a little further first before we, what could we pull out?
X cubed.
So you could pull out x cubed, negative 2x what? Squared plus 8 over x cubed times. We already know the original function is not defined for x equals 0, so canceling this out is okay. Negative 2x squared plus 8 all over what?
X cubed.
X to the 5th.
To the 5th, right.
X to the 5th, or we pulled out the x cubed. Okay, so now we're looking for the critical points. That's going to where x is equal to 0, right? And also where negative 2x squared plus 8 is equal to 0. So that's where 2x squared is equal to 8.
That's where x squared
Right.
is equal to 4.
X squared is equal to 4, so x is equal to...
Plus or
Whenever you've done a derivative like this, whenever you've done work like this, and you end up with a nice answer, that's a good sign, right? So what do you need to test here? You have 0, 2, and
Negative 2.
negative 2 as your critical values. These are not points because... They're not points because what?
Because
You don't have y values. 2 is not a point. So we have x values and fx. What's our derivative? We simplified our derivative to this, right? So here's our derivative. So if you plugged in, I don't know, let's plug in 1. What happens when you plug in 1 into this? We know these are zeros for the derivative here and here and here. If we plug in 1, what do you get?
positive.
What do you get? It's
Positive
positive.
over
That's
positive.
correct. Let's plug in negative. What do you get? What do you get when you plug in negative 1?
Negative.
You sure?
Yes.
Bottom's negative and the top is?
Positive.
So it's negative. That's correct. So this thing is negative. Let's plug in a billion. If you plug in a billion, it's going to be negative on the top and positive on the bottom. So it's going to be,
Negative.
and then it's going to be positive over. Do you agree with that? Now, so we know where is it increasing. You have to write this down. You know it's increasing from negative infinity to what?
2.
Negative 2. Also from 0 to, and also from, oh, that's it, right? Sorry. And where is it decreasing? Negative 2, 0, and to infinity. Exactly. So we did increasing, decreasing. Now, that naturally leads into, are these mins or maxes? And we know it goes positive, negative, so this is a max, min, and
Max.
max. So where is that minimum? That minimum is at 0 what?
It's undefined.
Oh, it's undefined, not defined. So it's a what? It's an asymptote. Okay, good. So it's not actually a min. What about the max? Negative 2, whatever the value is, and where else?
2 whatever the value.
2, whatever the value is. Now the original function is this thing. Plug in 2, what do you get? 4 minus 2 is 2. 2 over 16 is?
1/8.
1/8. So when you plug in 2 into the original function, you get?
They're both 1/8.
1/8. And when you plug this one in, what do you get?
1/8.
1/8. Is that possible?
Yes.
Absolutely. Definitely.
Well, we know it's even, so
Bingo. Awesome. Anchoring idea. That's huge. Okay, so we have mins and maxes. What's next?
The inflection.
Concavity inflection points. Exactly. So for concavity inflection point, we need to look at the...
second derivative.
What was the first derivative? It was what? Negative
2x.
2x squared plus 8 over what?
X to the 5th.
X to the 5th. So f double prime of x is going to be low d high plus high d all over what?
Low squared.
Low squared, x to the 10th. So now we're interested, what are the critical values there, correct? And what are the critical values there? What's one of the easy ones?
0.
0. It's undefined at 0. That's great. We're pretty much guaranteed we guarantee we're not going to cancel that. We need to know where the numerator is equal to 0. What is the numerator? It's going to be negative 4x to the 6th minus 10x to the 6th plus 40x what?
To the 4th.
40x to the 4th. We want that equal to what?
0.
0. We can combine two things and get negative 6x to the 6th plus 40x to the 4th equals 0. What can we factor out of that?
4x. X to the 4th.
I like factoring out negative 4x to the 4th. I just like getting the negatives out front. We can actually, no, let's just factor out 2 to keep fractions out of it. If we do -2, what do you end up with? 3x
3x squared
to the second, yeah, plus what? Or minus what?
minus 20.
20 equals.
0.
So we already had the 0 there, so what are we looking at? 3x squared is equal to 20. So x squared is equal to 20 over 3. So x is equal to plus or minus mathematical of
20 over 3.
20 over 3. Exactly. So that we know one of them is going to be square root of 20 over 3. And this one's going to be negative root 20 over 3. And remember, we're just interested in the sign, correct? The denominator is always going to be what? Always what?
0. That was going to be defined?
For any value you put that, it's either going to be undefined or it's either 0 or what? Always positive if not equal to 0. Can it ever be negative?
No.
So if we're looking at the overall sign of this fraction, we just need to look at the
Numerator.
numerator. Did we actually simplify the numerator?
Yes.
Yeah, what was the numerator?
-2.
This thing, right?
Yeah.
That was the numerator, right? So we're looking at the sign of that. Let's plug. Is that greater than 1?
No. Yes.
Yeah, it's greater than 1.
Yes.
Yeah, because 20 over 3 is greater than 1, right? 20 over 3 is like 6. Square root of 6 is going to be like 2 point something, right? Okay, so if we plug in 1, is it going to be positive or negative? So this is x, and this is the second derivative of x. If we plug in 1, what's it going to be? These are 0, right?
It's going to be positive.
It's going to be what?
Positive.
Really?
Yes.
If you plug in 1, is it going to be positive? Yeah.
Yes.
-6 plus 40 is? Yeah.
Positive.
I agree. We did? Where?
Or it says -4x to 6 minus 10x to 6. Wouldn't it be 16?
Oh, you're right. Yes, you're correct. It would be. This should be 16. Does everybody see that? Does this make our answer a little bit nicer? Does it make it nicer?
Yeah.
Good catch there, Maddie. Yeah, what can we can factor out the -4. What do we get now? -4x to the 4th times what?
4x.
4x squared.
I think 14.
14. Wow, we're just not doing well on this algebra thing today, huh? 14. So we still take out what?
Good.
Good math. Yeah. Well, that 1 should still help, hopefully. So what do we end up with? -2x to the 4th times what?
7.
7x squared minus
20.
20. It's similar, right? Is that correct?
Yeah.
Are we okay?
Maybe.
Maybe. So we know that x squared is equal to 20 over
7.
So x is equal to plus or minus 20 over 7. Now, is that greater than 1?
Yeah.
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 So this is root. Yeah, did we make a mistake? Yeah?
When you find derivative, it's low d, high minus.
Oh, wow! So can we just have a collective high five that we're not doing so well here? Let's just high five here. Ready? 1, 2, 3. Snap! Okay. So if we subtract that... Ready? So this is what we need to do here. Well, this is good. We're eventually catching this stuff. I'm happy. If you see these things, definitely point them out. Thank you for pointing these out. That's not cool. We're just not doing well as a group here today. So what does it actually become in the numerator? -20x to the 6th. That's -4x to the 6th stays the same, right? -4x to the 6th. Plus what? Plus 10 to the 6th minus what? 40x to the 4th.
That's what we started
Yeah,
with.
so it is going to be.
Well, it's not quite. This turn. The sign is different though. Look, hold on. This is 6x to the 6th minus x to the 4th equals. So we can factor. It's going to end up.
It's going to end up being 3.
It's going to be the
20 over
same.
3,
Yep,
yeah.
it's
So we
3.
got it, but
Well, yeah, we got it, but in
The
this case,
wrong way.
could it have collapsed the whole thing?
Oh, yes.
Oh, yeah, it absolutely could have. 3x squared times what? What is it? We don't want 2. We take out what? Instead of
2.
3, we take out 2, right? 3x. It does, but it could have blown up. It
3x
could have blown up.
To the 4th, not 3x squared.
3x to the...
No, you need 3x to the 4th. Or 2x to the 4th.
There we go. We want 2x to the 4th. So it's going to be x
Squared.
minus
20 at 20.
20. It's just 20, right? It's just 20
Yeah.
equals 0. So we end up with the same thing. X is still plus or minus.
Root 20 over 3.
So we found 3 mistakes and ended up back at the exact same thing. That's cool. I love, in algebra land, like, well, if it doesn't matter, we got the same. Well,
Yeah.
so if we plug in the 1, are we still at positive? Yes. Oh, no.
no,
Wait.
we're not.
No, this is where it changes, though. This is where it changes. If we plug in 1 there, what's the first derivative going to be?
Negative.
Negative right here. If we plug in -1, what's it going to be?
Negative.
No, it's still negative. Look, the 6 is always positive, and that's always positive. What's 6 minus 40?
Negative.
Both negative. What happens if we plug in a billion, trillion, quadrillion? It's a huge number. What's it going to be? Positive. Because that what happens to that x to the 6th? It gets huge. Does it matter what that x to the 4th is, even if it's 40 times it? No. What happens if we plug in negative something huge?
Same thing.
Positive, right. So here's the deal. We know that inflection points are going to occur where?
Negative root 20.
20 over 3 and
Positive.
positive root 20 over 3. But those aren't points. Those are the x values for that, okay? So ready? Your homework tonight is going to be to finish this one. And I will add in the page number and